Hello everyone, and welcome to today's chem lesson. Today, we are going to look at our reactions and try to determine what the different reaction types are. Looking at some examples and seeing if we can recognize what type of reaction something is based on the pattern that we see written for us. Now there's a couple of different types of reactions here. We're really going to look at these five: synthesis or combination, decomposition, single replacement, double replacement, and combustion. Each one of these five reaction types corresponds to a pattern that we can see when we look at any other reaction. So let's expand these out and take a closer look. A synthesis reaction or a combination reaction is exactly what it sounds like. Two or more things come together to make one thing. Right? Now, we're going to start using words like reactant and product to talk about things in reactions. Reactants is everything on the left side of the arrow, and products are everything on the right side of the arrow. So for a synthesis or combination reaction, it's multiple reactants combined to make one singular product. That can mean two elements come together to make one compound. It can mean two compounds come together to make a bigger compound. It can mean an element and a compound come together to make a compound. As long as there are multiple reactants coming together to form only one product, you have a synthesis reaction. It doesn't need to be just two, like we have in this example here, or we can have three things coming together, or more. We could have 4, 5, 6, 7, 8, no matter how many things you have, as long as they combine to make one product at the end, you have a synthesis or combination reaction. Decomposition is the exact opposite of synthesis. It's one reactant breaking down into multiple products. And again, there's really no limit to a decomposition reaction. It's not going to look just like this every time. You can have a compound breaking up into two other compounds. You can have a compound breaking down into the elements and another compound, right? You can have it just breaking down into elements on its own. Right, as long as you start with one reactant and end with multiple products, you have a decomposition reaction. And those are our two simplest reaction types, right? Either a bunch of things make one product, or one reactant makes a bunch of products. Single and double replacement are a little bit trickier, more because the pattern is a little bit tougher to see. When we look over at a single replacement reaction, one element by itself is coming in to replace and kick something else out of a compound. So in this case, Q replaces R in the compound, and we end up with R by itself and Q as a part of the compound. we're going to see this a lot with ionic. Here, silver comes in and replaces sodium. Silver takes the spot in the compound, sodium stays outside by itself. Right, and since we're not looking for the way the reaction looks, and we have to focus on what's actually happening in the reaction, it makes it a little bit tougher to keep track of. But if we're looking and we see an element by itself that ended up inside a compound, that's a pretty good indication that we're looking at a single replacement. A double replacement reaction is similar, right? It's the complement to a single replacement. But now instead of one element replacing the other, it's a swap. It's two elements replacing each other, or two ions replacing each other. And in this case, the M and the G replace each other. It was F paired with G in the beginning. It is F paired with M at the end. So the M replaced the G. It was L paired with M in the beginning. It's L paired with G at the end. So the G replaced the M. A double replacement. And again, just like for single replacement, we have to look at what's actually happening within the reaction before we can make our decision. It's not just looking at it and saying, okay, one reactant, multiple products, that is decomposition. Right? We have to pay a little bit more attention to what's happening within the equation before we can classify it. Now our last type of reaction, our combustion reaction, is a little bit on the special side, because these are actually compounds and elements, right? I didn't just write random letters. For combustion, it's a very, very specific type of reaction. It is a hydrocarbon with oxygen burning to make water and carbon dioxide. Combustions are really easy to identify because they all have this string at the end. Right? Oxygen is a reactant, water and carbon dioxide are the products. Now I put an X and a Y down here because you could really have whatever hydrocarbon you want. C2H4, C2H6, C3H8. Right? These can change, these numbers. But this bit is always going to stay the same. It's always going to be hydrocarbon plus oxygen to make water and CO2. Let's try some practice. Here, we have 3 different practice problems. What type of reaction is A? Synthesis, decomposition, single replacement, double replacement. What type of reaction is B? Synthesis, decomposition, single replacement, double replacement. What kind of reaction is C? Synthesis, decomposition, single replacement, double replacement. Right, so it's 3 questions here for you to answer. We're going to go over them all at once, so take some time and try to identify what these 3 equations are. these three equations, when we look at them, we get A is a decomposition reaction. You have one reactant breaking down into multiple products. B is a single replacement reaction. The zinc replaces the hydrogen. So now the zinc is in the compound, the hydrogen is outside of the compound. And C is a synthesis reaction. Multiple reactants combine to make one product. But that's not actually all we're here to talk about today. Today we also want to look at single replacements just a little bit more. We want to know if a single replacement will happen or not. How do I know if I'm looking at zinc plus HCl if zinc will replace the hydrogen, or if I flip it? What if I do this way? They can't both happen. I can't have both of these things happening because then our reaction's never going to stop. And so when I'm looking at something like this, where I'm trying to choose between zinc and hydrogen, which one of these reactions is going to happen, I'm going to use table J, which is our activity series. The activity series lists the elements, right? It lists some metals in a column here, and it lists some nonmetals in a column here. It lists them from most active to least active. And what this means is that elements that are more active, elements that are higher up on the activity series, are better at replacing other elements. Right? Lithium will replace any element that is below it on the activity series. Aluminum will replace any element that is below it on the activity series. Lead will replace any element that's below it on the activity series. And so if I'm looking here at these two elements, I've got zinc and hydrogen. Zinc and hydrogen. Zinc will replace anything that is below it. So zinc will replace hydrogen. Hydrogen will replace anything that is below it. Hydrogen will not replace zinc. All right, this acts as like a totem pole, a ranking system. Lithium is the best replacer. Lithium can't be replaced by anything on this table. Rubidium is a fantastic replacer, but it could be replaced by lithium. So on and so forth. And so when we're trying to decide if a reaction is going to happen or not, we're going to find both of the elements involved on table J and C. The higher one will be in the compound at the end. Right? Zinc will replace hydrogen. Hydrogen cannot replace zinc. The same thing goes for our nonmetals. If we're looking at nonmetals, they function the same way, right? Fluorine is going to replace chlorine, bromine, and iodine. Chlorine can replace bromine and iodine, but not fluorine. Bromine can replace iodine, but not chlorine and fluorine. Iodine can't replace anything. Let's take a look at some practice problems with this. will this reaction go forward? This reaction is the one that I used as our example on the last slide. Right. When we look, zinc is trying to replace hydrogen. Zinc is higher than hydrogen. And so zinc will replace hydrogen, kicking hydrogen out. This reaction will go forward. Question in the chat about what the subscripts are for. These tell you the state of matter. Right? We talked about this way back when in Unit 1, right? S for solid, AQ for aqueous. Right? They don't have any bearing on this problem, but it is something that is very often written alongside reactions. Right? Telling you what type of phase of matter it's in. How do we know which elements are replacing each other? Right? Let's look. Zinc, hydrogen, and chlorine. There's 3 elements here. These are our 3. Can chlorine interact with zinc or hydrogen? No, it cannot. So the chlorine is not the thing that is being replaced here. Right? They need to be in the same column, right? They need to be comparable for us to try to replace them. Right, so we have to be looking at things in the same column. They have to be in the metal side, or they have to both be in the non-metal side for it to work. Let's try another. Copper and hydrochloric acid. Will copper replace one of these elements? Yes or no? The right answer here is no, this will not happen. Here's hydrogen and copper, and for safe measure, chlorine. Right? Chlorine is not the thing we're looking at here. Will copper replace hydrogen? No, copper can only replace silver and gold. Right, so this reaction will not go forward. Why are these the only non-metals? Why are these the only metals listed? The answer there is because if we included all 118 elements, this would be a line that went down for 4 pages. These are the most common metals and non-metals, right? The periodic table, the reference table, is all selected information. It's not the complete works, right? The complete periodic table, the complete reference table is a book, right? For our Regents level chem class, we take selected information, some of the most common things to see, and we use just those. Let's try 1/3 practice problem. Will this reaction go forward, yes or no? Good. Here again our answer is no, this reaction will not happen. Here's zinc, here's iron. Sulfate SO4 is nowhere to be found anywhere on this table, so it doesn't even come into play. But iron cannot replace zinc, which means this reaction does not happen. If you mix iron, solid iron, and aqueous zinc sulfate, literally nothing happens. They just sit there. The activity series comes back and is super important when we start looking at oxidation and reduction in our electrochem unit. But that is a topic for another day. For now, I'm going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.